So thank you, Professor, for your introduction. As said, I'm Tina Peternel, and together with my colleagues from Geological Survey of Slovenia and from Faculty of Civil and Geodetic Engineering, we prepared a presentation with the title Implementation of Multidisciplinary Approach for Determination of Landslide Hazard in the case of Koroška Bela settlement. So today's content of this presentation will be in the beginning some background of the research work. Then I will continue with the presentation of a study case. I will go through the methodologies, and in the end, my colleague Jož Sodnik will present results of modeling of debris flow, and then we will conclude with some conclusions. So Slovenia has very hill slope morphology, quite complex geological conditions, and also very climatic diversity. So these are all factors that contribute significantly to the susceptibility of different slope mass movements. So here we have our national landslide susceptibility map. And from here, it can be seen that 1/3 of Slovenia territory is highly susceptible to the landslides. Meanwhile, debris flow susceptibility map show that around 15% of 15% of Slovenian territory is prone to debris flow events. So consequently, 1/5 of Slovenia territory is of Slovenia population actually lives in very susceptible areas that are very susceptible to slope mass movements. So the observation of this kind of events and monitoring is crucial for reduce hazard in the future. So our study case is located in the northwestern part of Slovenia, in Karavanke Mountains, and is located about the village Koroška Bela, which has around 2,000 inhabitants and quite developed infrastructure and industry. So these slope mass movements about this village actually pose a direct danger to this village. And this was the main reason that we observed that area in detail. So based on the field investigation, we considered that this hinterland of Koroška Bela village has two most active landslides, and this is landslide Čikla and landslide Urbas. So also historical sources describe that this village is known to have experienced several debris flow events in the recent geological past. So the most recent one occurred back in 18th century and caused destruction of village and cultivate areas. This village actually today lies on the debris fan deposits. So here is our geological map of this hinterland of Koroška Bela. So I won't bother you with the detailed of geological detail, but I would like to highlight that the main active areas are related with the finely grained clastic rocks that are tectonically deformed and high weathered. So this is the areas where we can find the most active parts. Also, I would like to highlight that this area is part of the Košuta fault zones, and all these are the reasons that this area is very prone to different slope mass movements. And also here we can see that this is alluvial fan, and now today here it's totally built, and today here lives around 2,000 people. So one of the landslides are Landslide Urbas. So the length of this landslide is around 400 meters with a width of 300 meters. The area that covers this landslide is around 85,000 meters. So here the first picture, actually we can see it's a view to Urbas landslide. Here is the main scarp of the landslide, and here is the body. And here is the opposite view. So from the Urbas landslide, we are watching this alluvial fan over Koroška Bela village. So the activity of this landslide can be recognized on the field. So we have a very ups and down terrain with a lot of erosion slumps. Also, we can find numerous of these kind of cracks, open cracks, and here we can also recognize the bedrock of this landslide. So this is the permo-carbonous clastic rocks. There are a lot of ponds and also subsidence of the local road. Also, we can find curved trees that are also a typical evidence of active landsliding. There is another landslide, landslide Čikla, with a length of around 130 meters and with a width of 100 meters. This landslide covers quite smaller area of around 8,000 square meters, but even though it's considered to be more active, as you can see from the picture, there's a lot of talus material that can be mobilized into the breeze flow, and this part really presents a direct danger for underlying village. So because of that, in order to assess the hazard for underlying village, we applied a multidisciplinary approach using different methods. This is the view of these methods that we applied. So we did the engineering geological map of the whole hinterland in order to recognize the active parts. We did a detailed engineering geological map of landslide Čikla and Urbas in order to recognize geological units and to define sliding surface. We did 7 boreholes. The depth of these boreholes was around 40 meters, so they were quite deep, and some of them were equipped with the inclinometer or piezometer. So in order to do a groundwater measurements, we applied piezometer, and now we have real-time periodical measurements of piezometers. We are also doing inclinometer measurements in order to recognize sliding surface, and we also applied some slug test. Then to assess the thickness of the lithological units and to assess also the sliding surface, also we applied geodetics, geophysical models. We applied seismic refraction method and electrical resistivity tomography. So in landslide Čikla we did 2 cross-section, meanwhile in landslide Urbas we did 3 cross-section of geophysics methods. So based on that, so we did reconstruction of landslide body, and we did estimation of the thickness of landslide material, and we assess volume for landslide Urbas and for landslide Čikla. And as you can see, the volume calculation for Urbas landslide was around 900,000 cubic meters. So there's a lot of potential material, and based on this method, we also did a volume calculation for Čikla landslide, and this was around 140,000 cubic meters. I would like to ask Jož to come back.
5 minutes, Jož.
Uh-huh.
That's okay.
Thank you. So far,
we have potential landslide volumes. And now our job here was to determine what can happen if this landslide trigger and turn into debris flow, and of course when they travel down to the densely populated Koroška Bela fen. We use Flow2D software. The topography was based on the LiDAR-derived digital terrain model. And to get from landslide to debris flow magnitude, we firstly did some hydrological modeling to get the watershed areas of each landslides and to get the available water that can help turning these landslides into debris flows. So when we have material, the volume of material, the volume of available water, we did some geotechnical research to determine the saturation level of the material on field. Then we had to assess the geological characteristic. We chose volume concentration 45%, and the runoff hydrograph, we used two approaches. One was to assess the maximum discharge, peak discharge, which was used proposed with method from Professor Rickenmann, and the shape of the hydrograph was adopted after the 2000 event in Lok pod Mangartom. So these are our main input data from the Urbas. We can expect 340,000 cubic meters of debris flow with peak discharge over 4,500 cubic meters per second. On Čikla we have smaller numbers, but still big for this torrent. So we used two models. One was with the grid cell 10 meters from the source areas, both source areas down to the fen. And the other one was more detailed with grid 5 meters concerning only the fen. And these are the results. On the left hand you can see the results from Urbas, potential debris flow. As you can see, we get around 7 meters of maximum depth on the upper part of the fen, which is definitely a catastrophic event for this area. And on the right side you can see from potential debris flow from Čikla landslide. We have also around 4 meters maximum depth, so it's both of those scenarios are catastrophic for this, would be catastrophic for this area. So now I'll hand it back to Tina. Thank you.
Thank you. So just to conclude our presentation, so engineering geological mapping showed that in the hinterland of Koroška Bela there are more than 20 active landslides that can present a direct risk to the settlement. So like I said before, presently there's 2,000 people in the area of alluvial fen. And with this risk in mind, landslide monitoring, debris flow modeling and assessing hazard is crucial for future development of mitigation measures and for effective disaster risk management. So this study reveals that Urbas and Čikla landslide are deep-seated landslide, and both have potential to mobilize material into debris flows. And also this research proves that mechanism of these both landslides are related to the geological and tectonic conditions that are affecting rocks, which are highly deformed, and consequently they are very prone to fast and deep weathering and also to slope mass movements. Also, surface and underground water circulation in the wider landslides area and weak geomechanical properties of lithological units of the study area are very important mechanism of these landslides. So the modeling results show that potential debris flow with previously mentioned magnitudes would have a catastrophic consequence for this village. Simulated depths of potential debris flow exceed 5 meters in some density populated parts in Koroška Bila. So, therefore, application of mitigation measures is very crucial for this part of Slovenia. So, thank you for your attention.